Hi, and in this video we're going to talk about what you need to know for the fifth question in the UILCS test that typically goes over Boolean logic. So there's multiple tools for Boolean logic, or there's multiple Boolean operators that we can use to control our logic. For instance, we have the AND or NOT operator. So if we're looking at the AND operator, which is signified, by 2 ampersands, this is also known as the logical AND. And what the logical AND does, that says logical AMD. What the logical AND does is it takes so it'll take two booleans, say boolean A and boolean B, and will return true. So it will output true if boolean A is true and boolean B is true. So if we look at a truth table for AND, let's say we have A, or here, I can just zoom in here and just do it. Let's say we have A, B, and then what AND gives us. So before we start this, I want to quickly just denote something. In terms of computers and machinery, you might see truth being represented as 1 and false being represented as 0, because computers read everything in binary, right? So when they read these logic gates, they can't read true, they can't read false, but they can read 1 and they can read 0, because as we discussed in the base video, all those videos back, 1 and 0 is binary. So for our instances, 1 will represent true and 0 will represent false. So when A is false and B is false, our AND returns 0 or false, which makes sense because AND will only return true if both are true. So if A is true and B is false, that's still going to be 0. If A is false and B is true, that's still going to be 0. And only if A is true and B is true are we going to get 1 returned, or true. And I'm just writing false, 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 true so you can see it better. And it's called a truth table. What we set up here, where we have the, I guess, kind of conditions on this side, the booleans on this side, and then the expression, the final outcome. And then the final outcome. It's called a truth table. I've seen them ask about it like once or twice. Just make sure you understand this format. And I'll keep using them for the other ones too. So that's and I can represent this in code too. So for an example here, true, false. So when I run this, you'll see we're going to get false because, as I discussed earlier, and is only true when A and B are true. So in this instance, A is true but B is false, so it's going to be false. If we make them both false, if we made B true and A false, you'll still see we get false. The only way we're getting an output of true here is if they're both true. So, as you can see right now, yeah. So for AND, the way AND works is AND returns true if both A and B are true. So in order for me to demonstrate AND a little bit better, let's look at it in context of this example with agent height. So let's say you're writing a program, and the goal of the program is only let users ride this carnival ride, let's say, if they are above 15 or above 16 and are at minimum, I guess, 48 inches tall. It's like, what, 4 feet? So we can write that with an if statement. If age is greater than 14 and, and this should be, we said 16, and height is greater than 48.0. If this is true, then let's just print out you can ride. And if it's not true, if it's false, then let's print out you cannot ride. And just real quick, I don't know if we discussed this yet. This is the syntax of an if statement. So if statements are kind of like this, if condition, and you have little brackets, right? So if the condition is true, then the code inside here will run. Otherwise, the code outside here. So pretty much if the condition is true, the code inside here will run, and then the code outside here will run. But if the condition is false, we'll skip this entirely and then run outside code. Now what people can do is they can add an else condition. And else says if this code is false, so if this condition evaluates the false, don't run the outside code. Code inside else will run. So run this code and then go outside and continue whatever the program is going on. Then you can also have an else if. And an else if is, it's pretty self-explanatory. It's saying, oops. An else if is saying, if my initial condition is false. If this is false, check if this second condition is true. If it's true, then code inside else if will run. Otherwise, move on to else, run that, and then outside code will run. And you can have as many else ifs as you want. Okay, so like if we run this example, you'll see we get true. Or sorry, we'll get you cannot ride because we're 14. Even though we're meet the height requirements, we're too young to ride this ride. And because we're using the and operators, both conditions have to be true for us to get a value of true. Right now this condition is always evaluating to false. As you can see right there, it at least says false. Okay, that's the and operator. Let's move on to the or operator. And again, this is the logical or. I don't know if I specified that this and up here is, okay, I did. That's the logical and this is the logical or. Okay? So, the logical or is if condition A or here, we can just write this. If condition A or condition B is true, then I'm true. So unlike in and, when they both have to be true, in or, all it requires that one is a true at least. So if we look at the truth table for and, or for or, we'll have A here, B here, and then I'll have F for output. Most time you don't see it written like this, you'll see like some letter like, I think my teacher used F. We can make it Z though, because I've seen Z be used before. So we'll use Z. So this is the truth table for an or. And so if we have a 0 here and 1 here, or a 0 here and 0, we're still going to get 0, right? Because or is only true. Or is true as long as one of the conditions is true. But here both of our conditions are false, so this can't be true. But if A is 1 and B is 0, well now we have 1. So we're getting an output of true. This was false. This was true. Because remember that 1s are true and 0s are false. Because, look, we said condition A or condition B is true, then the whole thing is true. And your condition A is true, doesn't matter that condition B is false. As long as one condition is true, the whole thing is true. So same principle applies here. And then if both things are true, well, that's even better, and that's also true. Because it's at minimum, one has to be true for the whole thing to be true. Okay, now let's look at this or in code. So if I had Boolean A is equal to true, and Boolean B is equal to false, then if we print out A or B, well, this is going to be true because one of them is true. But if we made them both false, now it'd be false. If we made this one true, it'd be true. So you're just kind of seeing, right? For or, as long as one is true at least, or as long as one of the two conditions is true at least, then the whole expression, will be true. So in context of our previous example, let me loop back the code. Let's say we had this variable called signed waiver. And I'll take all this information and just dump it into another Boolean. So Boolean is eligible. I'm going to store all this stuff. And then we can say you're able to write if you're eligible, which means you meet these conditions, or you signed the waiver. So or signed waiver is true. Now, because when we run this, you'll see that I'll be able to write. It'll say you can write. Even though I don't meet is eligible, even though if we print out is eligible, let me just print that out for clarity, is eligible is going to be false, right? It's going to print out false because I'm not above 16 and we use this with an and, so both conditions have to be true. Because I have my signed waiver is true, in the or expression, because this condition is true, it doesn't matter that this condition is false. The whole thing will evaluate to true. So that is the or. Now let's move on to the not. And the not is pretty like self-explanatory. It's just kind of like the opposite. So the not operator, also known as the logical not, will take whatever value you give. So if you do not true, it'll be false. If you do not false, it'll be true. And if I store this in a truth table, we'll only have one variable this time. And then we'll just have our output over here, z for output. Well, what? I have 1 or 0. Well, if we're doing this in a not, that 1 is going to swap to 0 and that 0 is going to swap to 1 because it just flips it, right? That's what the not does. And then, so if we try and apply that to our current, so let's look at the not in code. So Boolean a is equal to true. Well, let's print out not a. If you print out not a, we're going to get false because we're having a as true, and then not true will be false. Because the not operator swaps the value, kind of like switches it around. So if you're taking the not of a true, it's going to be false is your answer. And then not false is going to give you true, and it's kind of like just say it out loud. Not something that's not true is false, and something that's not false is true, like in our normal day-to-day language. So then applying that to the situation, back to this problem set. So what if we said signed waiver, we put a little not here. So let's say not signed waiver, which doesn't really make sense for a carnival ride, but I guess we're like, I don't know, we're that one euphoria ride. Well, if you ride this, now we're gonna get you cannot ride because it's eligible is false, but now because of this not, the signed waiver, the second condition is gonna be false because we're saying signed waiver is true and not true is false. If we made, let's say we made this one true and we made ourselves 18. Well, now we would get true because this expression is true. And real quick, now we've covered nots and ands, we've covered ors and ands. I want to cover short circuiting. So short circuiting. So when you have an expression like this, true or condition 2. Well, Java already knows this whole thing's going to evaluate the true because you have a true here, and for or, only one of the conditions have to be true. So after reading the first condition, Java's going to just immediately go, like if this is an if statement, it's pretty much, or here, something like this. After reading this first true and understanding that we have an or, Java's not going to read the second condition. It's just going to evaluate the whole expression to true. And this is vice versa if we had false and an and. Because both conditions have to be true for an and, if automatically we know when the first condition is false, then we know the whole thing will just evaluate the false anyways. So what Java does is it sees that false, sees that and, it completely ignores condition 2 and will return false. Now why is it important that it ignores condition 2? Well, if condition 2 is something like this, like true and 1 over 0, well, if we don't know, this actually returns an error. But because, this should be true or, I'm doing straight short circuiting here. True or 1 over 0, this expression actually never gets evaluated. This right hand 1 over 0 never gets evaluated because Java sees it's true, Java sees it's or, it completely skips this and just will return true. Don't believe me? Let me show you it right now. So we're pretty much done with this example, so I'll delete it. Let's print out true or 1 divided by 0. If I run this, you'll wait. Oh, sorry, because 1 divided by 0 is not not a condition. Just keynote, your condition is the key what I've been saying, an expression that evaluates to true or false. Note how 1 divided by 0 did not apply as a condition because it didn't evaluate the true or false. But 1 divided by 0, we checked if that is equal to 0. Now this is a condition because this could evaluate the false, this could evaluate the true, depending if 1 divided by 0 is equal to 0. And don't worry about this, we'll talk about this in literally like almost next video, or next video. So running this, you're going to see that, hey, we didn't get this error. We didn't get numeric, at least says here, numeric overflow in the expression. But we didn't get that. Okay, then you might be thinking, okay, I'll just swap it around now and then we'll be fine. Right? If you didn't get it then, we're not going to get it now. But actually, we're going to get an error now. Arithmetic exception divided by 0. Because the whole reason we didn't get that error originally is because Java evaluated the true, saw it was an or, skipped this entire second condition, and just outputted true. So you can kind of look at the same thing with an and. If I made this false and made this and then I ran this, well, we're going to get false. We're not going to get this expression or this error because Java's going to see it's false. It's going to see we're working with and it's going to evaluate false. So I've been discussing when I talked about and, or, and not, you saw them with this syntax, right? Well, that's not the only way you can express them, because in computers, we have this concept of an AND gate, and OR gate, and a NOT gate, which I'm going to talk about. So, an AND gate works exactly the same as an AND. It's the exact same idea, you have to understand what it looks like. So we'll have one line representing condition A, another line representing condition B, so this can either be 1 or 0, and this can either be 1 or 0, and then it'll connect to this kind of like semicircle structure, and it'll return output. So if you think about it, we have A right there, B right there, and we're ANDing it to get our output. Okay, so that's the AND. Same concept with an OR. You have one line for your condition A, another line representing your condition B, and you kind of this weird arrow looking shape is how I describe it, with your output coming at the end, right? And well, this is just A or B, right? It's going to take A, or with B, and it's going to return whatever that output is saved to Z. Just like we saw with our truth table examples, how the final outcome was saved to Z. It's kind of a bad example. Yeah, Z, right? I don't know if Z is official terminology, that's what I'm using. And then in addition, we have not, so same idea. But remember, not only takes one thing, so we're gonna have A. And then it's just gonna return out, this should be there. Should be like right here. Well, let me actually make this look good so you know what I'm talking about. So what this will do is we'll just run not A. And I don't know why I put false here. And then whatever that expression is, we'll just give you output. So expression run output. Your condition, it's just the exact same concept. We'll not it, and then we'll just store that output in C. So you could say Z is equal to not A. So the little bottom statements that I've written for these are things we can call logical statements. They're logical statements, they're just an expression, kind of like mathematical type. A and B is equal to Z. Because you can see that A and B, whatever output that is going to go directly towards Z. Same concept here. A or B is equal to Z, because A and B, whatever that outputs, whatever Boolean that outputs, whatever 0 or 1, will get saved to Z. Not A equals Z. I don't know why I wrote like this, left to right, but same idea. Whatever 0 or 1 is in A will get knotted and will be saved to Z. So that's something we call a logical statement. Now before we dive in, I just want to introduce what a logical statement was. But we actually have a few more gates I want to cover. Just as there was the AND, OR, and NOT gates, well, you can actually take this NOT and apply it to this OR, and apply it to this AND, and two new gates will form from that. The NAND gate and the NOR gate. So the NAND gate looks like this. It's taking in A, it's taking in B, and it's going to be the same semicircle with a little circle coming out, just like how in the NOT it had a circle coming out. Same idea, that circle's coming out here too. And this can be looked at in a logic statement as A and B knotted, like this. Again with NOR, it's going to be A, it's going to be B, and you can kind of already guess what this will look like. It'll look like this with a little dot here. And then you can say A or B. I don't know why I wrote B like that. So could have A or B is equal to Z, and A or B not. Just real quick, this little top bar I'm drawing is not. This is the same thing as me writing, for instance, which is probably more familiar what you'd be used to. This is the same thing. Putting this little bar over it just means you're knotting the whole thing. Okay? Now if we look at the truth tables for NAND and OR, so I'll draw NAND here and NOR here, you'll see they're very similar, or pretty much they're directly based off of the and OR tables. So we'll have A, B, Z. If this was a normal AND, let's say 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. That's a normal AND output. But this is not AND. So we're just going to knot all this output. And our actual output is going to be 1, 1, 1, 0. So this is NAND. It's not AND. Take the outputs of AND and you knot it. Same concept with NOR. So we have A, B in our truth table. Z, I don't know why that line's so squiggly, bro. 1, 0, or sorry, I like to 0, 0, 0, 1, 1, 0, 1, 1. So in an OR, this would be 0, 1, 1, 1. But in a NOR, because we're knotting it, it's going to be 1, 0, 0, 0. So that is NOR, that's NOR and NAND. And there's one last gate, or actually two last gates to talk about. XOR, exclusive OR, and then XNOR. So you can kind of already guess that XNOR is going to be not XOR. What is XOR? So if OR was one or the other at least, had to be true, right? Had to be true. And key word on that at least. This meant that you could have 1, 0 and then evaluate to 1 or true. You could have 0, 1 and then evaluate to 1 or true. That's perfectly square, bro. But you can also have 1, 1 and then evaluate to 1 or true. Because just at least one had to be true, which means both could be true, right? Both could be 1, then OR would give you true. Well, XOR, what I mean by exclusive OR, is that this doesn't count. They don't care about that at least. For XOR, one or the other has to be true for the whole thing to be true. It has to be either 1 0 or 0 1 to get true. So the truth table for XOR would look something like this. A, B, hit them with a Z, 0 0 1 0 0 1 1 1, and your output would be 0 1 1 0. So false, true, true, false. You can see that XOR is only giving true for these values. The ones that are true or false, false or true. But true and true or true is not counting that. 0 0 obviously not counting that. So it has to be like kind of exclusively or. It has to be one or the other. And we also have its symbol, which I can just show right here. So be represented like A, say this is A, this is B. You're gonna draw one line out and then another line like this. Yeah, I'm right, okay. I mean, it's a little bit more close together in the thing, but this is fine. Right? Why not keep putting F, let's see. And the symbol for XOR is gonna be this. A circle plus B. You can also view it as A in the computer. You might see it as A caret sign B. These mean the same thing. I mean, because real quick, I haven't really discussed it yet. There's numerous symbols people use to denote AND. I talked about this symbol, but some people also use the multiplication symbol. Why? Because, well, what's 1 times 0? 0. What's 0 times 1? 0. What's 0 times 0? 0. What's 1 times 1? 1. So you can kind of see how using the multiplication kind of mimics AND, right? People also use this symbol, this like kind of like weird A kind of looking symbol. For OR, people use this symbol, but people also use the addition. Why? Well, what's 1 plus 0? 1. What's 0 plus 1? 1. What's 0 plus 0 is 0, and then what's 1 plus 1? That's 2, but in binary you can't have numbers bigger than 2, so it would evaluate to 1. Even if you had 1 plus 1 plus 1 plus so on and so forth, in binary, that's just 1. And what's this? Well, this is just OR, right? So that's why people use a plus to represent OR. And it can also be denoted as this downward time. So you might see me switch through here. Not is represented by this side. It's also represented by this symbol I showed earlier. And I've seen it represented like this. So if we just have our expression A, right? Not A, and then this little weird symbol for not A too. And then lastly, an XNOR looks like this. AB, it's the exact same concept. We have a little dot here. So it'd be represented like this. Draw your line like this. Okay, that's our XOR. If you're looking at it as a truth table, XNOR. XNOR would be, if this is XOR, XNOR would be the opposite, right? So 1, 0, 0, 1. So now we're going to talk about some Boolean algebra. Boolean algebra. So we saw that expression. You know what a logical statement is. Z, or whatever, is equal to A and C. I'm going to use the multiplication symbol for and. So A and B plus C, maybe not something, whatever, right? You can have a bunch of expressions in here to make your logical statement. The whole point is all evaluates, then this can be a logical statement, right? And what would it be represented with? If we simplified this to A and B plus C, well, now you're looking at something like this. A, B, and that together, and then you take that output and then you OR with C. It's not B or C, then A, because if you remember from object precedence, and is logical and is over logical OR. Right? And then you just run like this. And I don't know why I drew that dot there, ignore me, bro. It looks like this, right? And you can kind of see if our expressions got really, really long, how big this would get, how much it would scale, right? That's way too big, and especially because we're building this stuff, we're using this for computers and stuff. We want to maximize efficiency and we want to maximize coolness. We just don't want our computers to be inefficient. So that's why there's this concept called Boolean algebra. There are all these identities we can use to take or all these identities slash laws that you can use to take all these really complex looking expressions and simplify them drastically. The identity law. So the identity law works like this. So we'll take a condition A, and if you're ANDing it with 1, well, we know it's going to be A, because that 1 will have no effect. It's an AND, remember? So we already know that one's true, so your whole output, your whole final answer is dependent on whether this A condition is true or not. So that's why you can say A times 1 is A. And also this makes sense from a math view, because we do 3 times 1, that's true, right, in math. It's kind of like you can do a lot of math equivalencies here. That's kind of why it's called Boolean algebra, at least I think. And then conversely then, if A times 1 is A, you can kind of view as A plus 0 is also A. And this makes sense too. It's another identity law for OR. Because if this other one's false, if your condition 2 is false, your final output, your Z, is completely dependent on whether A is false or true. Same thing here. If your second condition is true, for an AND, your entire Z output is completely dependent on whether A is true or not. These are your identity laws. And make sure you know the name, because they ask by name, bro. In addition, you have your annulment, or I'll say null. Some people say dominance laws. I call them null law. They're null laws. And it doesn't matter. So what this one says is, if you have an and you have a false, then you know your whole thing is going to be false, right? Your whole expression is going to be 0. It's kind of comes back to that sort of circuiting idea I talked about earlier. Conversely, if you have a condition A and it's ORed with a true, then you know your whole thing is going to be true, right? Because if you have an expression like condition A and false, well, you know for an and, both things have to be true. So automatically, you know this whole expression is cooked and it's going to evaluate the false. Same thing here. A or true, well, because of an or, just one of them has to be true, and you already have one is true, so you can just say that the whole expression is true. So that is the null law. It's pretty easy. Just this one is pretty straightforward. A times 0 is 0 because that's from math, but really understand like A plus 1 is 1. Kind of like, let's just imagine the output of this. It's always going to be true. And then what is true? If this expression is always going to evaluate the true, well, we've also called true 1. So that's why it's 1. That's where you get this 1 from. If you see in the 0, it's false, 1 is true. I don't think I have to explain that anymore though. I think y'all got that. Next, you have the idempotent laws. Idempotent law. So this one is pretty easy. All it's saying is like if you have condition A and it's ANDed with condition A, then your whole expression is determined on condition A, which kind of makes sense because these are the same thing, right? So if your A is false, false times false and false is false. If your condition is true, true and true is true. So it's really just dependent on what A is, right? Because A is literally the only thing in your expression. So like, what else can it be to figure out your final answer? You know what I mean? It has to be based off A, which is what all impotent law is saying. In addition, if you had A plus A, conversely, it's the same thing. Well, true or false, it doesn't matter. Your output is going to be determined on what A is, whatever this condition A is. So that's the idempotent law. The next law is the complement law. So what the complement law says is, if you have A and A naught, that's going to be 0, or false, which makes sense, right? Because even if your A is true, you're going to have true and false, which we said was false. And if your A is false, you're going to have false and true, which is also false. So no matter which way you look at it, you're going to get false as your output. So let me just delete all that real quick. Yo, not the button I was trying to hit, bro. And then conversely, if you have A plus A naught, this will always be true. Because at least one of these is going to be true. If your A is false, then you're going to have false plus true, which is true. And if your A is true, you're going to have true plus false, which is also true. And remember, false or plus is or, okay? A or A naught. A and A naught times is and plus is not. Okay, let's move on to the next law, which is the double negation law. So double negation is pretty simple. It's kind of like you've heard of it in math. Like if you have two negatives and you know how to cancel out, it's the same concept. So if I had A, and then I knotted it, and I took that whole expression and I knotted it, the knots would cancel out and you have A. And that's it. Moving on to the commutative law. And I guess if you want an expression, if A is false, we're going to have not false, which is true, but then you're going to not that and you're going to go back to false. If A is true, you're going to have not true, which is false, but then you're going to not that and you're going to go back to true. So no matter what you do, you're going to end up back where you started. Moving on, we have the commutative law. Commutative law. I don't even know what I'm saying, bro. Commutative law. You might have heard this word in math before. All it means is that the order of your operators don't really matter. Or I guess operand is the correct word. So all that's saying is if you had A and B, that's the same thing as saying B and A. If you have A plus B, or A or B, it's the same thing as saying if you had A or B, it's the same thing as saying B or A. And then that's just math. I think that makes sense. You have your associative laws. So what this one is just kind of like, if you're looking at something like this, A times B times C, well, if you just write that out plainly, that's A times B times C. And so then you could have this in parentheses, you could have that in parentheses. It doesn't really change the final outcome. Don't believe me? If you did something like this, 4 times 5, like let's say times 5, just like doing some math, and then you had 4 times 5 times 5, you're going to see it's going to give us the exact same outcome. 100 for both. So that's all that's saying. It doesn't really matter. A times B parentheses B times C is the same thing as parentheses A times B times C. And then we also have the same idea when it comes to addition. A plus B plus C is the same thing as A plus B plus C, and it kind of goes back to this law. If you think about it, in this law we said the order of your operands don't matter. So you can kind of view A times B times C as this. And by commutative law, you could kind of view it like as this, right? And then so if this was like this, well now it's like this. It doesn't really matter. All I'm trying to say is it doesn't matter. The order of operands doesn't matter. That's the whole point of these laws. Obviously, some things are true, like if you have B times A plus C, you can't write C times A plus B and call it a day. You can't do that. That's illegal. I would know the commutative and associative laws. I mean, I think they're pretty self-explanatory, but it's pretty helpful when it comes to like simplifying really big things, really big, weird-looking expressions. Moving on to the distributive law. Distributive law. So if we have the expression like this, A times B plus A times C, well, it's the same thing as A times B plus C, right? Like math. And yeah, that's just distributing it out loud. It's just distributing, right? If you look at A times B plus C, you distribute the A, you get AB plus AC, which is what we have right here. This and this match up. And I'm writing it with that weird side first because it's like more flattened, it's more like expressive side, is probably what you're gonna get on a problem. In addition, you have this A plus B times A plus C is the same thing as A plus BC. Same concept, right? If you multiply the AI, you're gonna get A plus B. Or if you want to multiply the A out, you would multiply the BC. Or if you wouldn't, it wouldn't really multiply. This one's kind of weird because there's no like mathematical equivalent to this. This one you can explain through math, which is what I did. I multiplied the A here and stuff like that. But this one doesn't work in math, but it works in Booleans expressions. So most things in Boolean algebra you can kind of relate back to math, but not everything. Like this, for instance, you just kind of have to know this. You just kind of have to see that A. You try to be able to take out the A, and you have to see it like this. One way I like to see is when I know I have something like this, and I know it's distributive. just take out the thing that's in common, take out the thing that's in both of them, and then whatever the middle operator is connecting them, that's going to be what I use here, and then whatever the opposite of that is what I'm going to use here. So in this case, I see that A is the same, so I'll take the A out. Then I see the middle operator is a plus, so I'll do B plus C, and the opposite of that is going to be an AND. Opposite, I guess opposite or kind of is an AND. You can look at it like that. Same thing here. A plus B times A plus C, I'll see A is in common. I see that the middle operator is a multiply, so I'm just going to multiply them together. Opposite of that is an add, and then that's how you get that. That's how I look at it. Luckily, I'm not good with distributing stuff. Okay, moving on to De Morgan's. So, De Morgan's laws. I'll give him his own section, he's kind of important. It's like the guy for computer science, bro. How many classrooms? If you've been in a computer science class, you've heard of this law before, probably. But all it is this. So not A, if you have something like this, where it's not A and B, it's the same thing as not A or not B. And then if you have not A or B, it's the same thing as not A, B. So you can kind of view it as taking this expression. This is how I view it. This is what makes sense in my head. You have your expression A and B, you're noting it. It's kind of applying the not to everything. So you're going to not the A. You're going to not the and make it a or. Which isn't really true because it's an and, but I don't know, it's kind of, if you can kind of mentally get yourself to see that, or connect it like that, even though it's a little bit of a logical fallacy, it can help. Kind of view it as swapping the operator, not nodding it, swapping it. And then you do B not. So you're kind of just nodding or swapping everything. Same thing here. You're swapping the operator and then you're nodding everything else. And that's how you get that one. And that's just De Morgan's law. You can kind of view it, I kind of view it as applying the not to everything, even though it's a little bit wrong, because you're not nodding the Boolean operator, you're just swapping it. But if that way helps, then do it. Do it every way helps, you know what I mean? And then lastly, we have the absorption law. This is the most goated, well, I wouldn't say most, but I would say it's one of the most goated laws to exist out of Boolean algebra. I might just say that right there. That and inputting. I've used inputting law. Anyways, so what this law is saying if you have A plus AB, or I'll write it in a better way. A or A and B, and they're in parentheses. It's the same thing as just having A. And then if you had A times A or B, that's the same thing as just having A. You can kind of view it the way, what you kind of look out for in this law is you have an A on the outside and then an A on the inside. And then your kind of like operators are different. Like it's an plus on the outside and then a multiplication on the inside. It's a multiplication on the outside or an and on the outside and then or on the inside. So the operators are swapped. And if you want proof for this, so we have true or, let's say we have this, true or true and false. Well, this is going to evaluate the false, but it doesn't matter because this is true, so the whole thing's going to become true. If this was false and this is false, it wouldn't matter if this was true because this is already false, right? And this is false, so your whole thing is going to become F or F, which is going to be false. So you can kind of see how the output changes when A is true, your whole thing is true, and then when A is false, your whole thing is false. Conversely, if A is true, and you have A, so you'd have, on the second one, you'd have true times true plus, right, yeah, true plus false. Well, this false wouldn't really be doing anything, because you'd have a true here, so it'd evaluate like this, and it'd evaluate like this, right? Conversely, if A was false, you would have false times false plus true, but it wouldn't really matter if this was true or this was false. It wouldn't really matter even if it's evaluated to true because A is false, so we're going to be ANDing it with a false, so your whole thing is going to become false. That is the absorption law. So those are Boolean algebra laws. So I think it'd be helpful for us to do a practice problem that we can use a lot of the laws in. So this is the whole expression we're working with here. So x or y knotted, or x or y knotted. This is a plus. And then the whole thing is knotted. So let's just start off by applying this knot to everything. Here you can see the double, I think it's called the double negative law. I can check real quick. Or double negation, same thing, bro. Just fancy app. I guess we can use double negation here. As you can see that this will negate with that, and you'll just be left with x plus y plus the knot of, or this whole thing will be knotted, x plus y knot. So we're just looking at this, right? We saw that you can double negate that to get x plus y, and now we're looking at this. Well, here we can use De Morgan's and kind of handle this. So we'd swap the operator, so it's become times, and then we'd apply all of we'd deal with this too. We use De Morgan's for this. So what? We knot all the variables, that'd be not x, not y, or I guess this case would be y, because that's already knotted. And then we swap the or to an and. So now our expression is looking like this. X plus y times x naught y. Now here might not seem evident what to do. So what I like to do in this case, sometimes you want to expand your problem, make it look a little bit more complicated, because then you might be able to find more laws you can apply. So if we multiply everything out, we're going to get x times x naught times y plus y times x naught times y. And for this one, you can see right here we have the complements law. So we can use complements. So we can use the complement law. I don't know why I said complement law. I was thinking 2's complement or something, bro. Anyways, if we do x times x naught, and because this is an and, it's going to evaluate to 0. And when we have 0 times y, we can use the null law, which would pretty much mean that the 0 times y will just evaluate to 0. And then here we are on this other side of the or. Y times not x times y, well, we can simplify this. And here, let me just drag this out because here it's trying to look at getting kind of messy. We're looking at this, right? You can simplify this using the commutative law and say it's written like this. That's not even how you spell law. It's okay. Y times x naught. And now you can use the impotented, or whatever it's called, bro. Idempotent. It's always like on the tip of my tongue type of law, but like you'll have multiple choice, you'll be fine. Idempotent, right? So now you can use this law to make y just become y times x naught. So you can write that as x naught y. Putting that back into our expression, here we can use the identity law to say, and this 0 pretty much just go away because we're doing 0 or, so the whole thing is determined based on this x naught y. So our final expression will look like this. Z is equal to x naught y. And that is an example of using Boolean algebra. Let me make sure I got the right answer. Was it x naught y? It was x naught y. Were all my laws correct? Hopefully. Null law, good. Identity law, good. Alright, cool. That was an example. We went through a lot of the laws there, not all of them. We didn't talk about distributive. Ooh, I kind of want to do one with distributive. And oh, we got to look at absorption. But here, let's say that for maybe a later time, like when we go over those examples, and when we do an actual coding practice of this stuff. But if you want more examples, bro, there are a trillion. There's so many Boolean algebra problems. Just what I would recommend is just having that screenshot or having the laws opened up. You can use this if you want. I'll like try and pan to all of them. It's a little bit chopped on my screen though. I guess if you want, you could take a screenshot of this and use it. Or if you've, there's definitely better photos out here, bro. Just use some better photo. I don't care. And then just like, yo, okay. And then just grind practice problems. Refer back to the laws when you need it, and you should be good. So we covered a lot of ground today. The last thing left to cover is bitwise operators. So bitwise operators. Here's how they work. So we talked about, if you remember me mentioning this idea of a logical and. Why do I have to specify logical? Because there's also something called a bitwise and. And the whole thing behind bitwise operators is that they work with binary values itself. So I know when I was doing my example, I was doing like 1 and 0 for and stuff like that, right? Well, I guess that's more applicable towards this bitwise version. When you're dealing with logical operators, you're dealing with trues and falses. When you're dealing with bitwise operators, you're dealing with binary, so zeros and ones. So if you look at the binary and, which is bitwise and, which is like this, it's the exact same idea. I'm not even gonna, I guess I could write the truth table, but you've seen this before, because I use this exact same idea when talking about logical. So 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and a 1 and 1 is 1. Now what makes this interesting is when it comes to actually applying this. So you'll see problems like this, 34 and 5. Well, what is 34 in binary? That's going to be what, tree? So that's going to be 1, 2, 4, 8, 16, 32. That's 34, right? And 5 is going to be 1, 2, 4, 0, 0, 0. Rest we can just assume as zeros, right? So because we're using and here, we're applying these same rules. So 1 and 1 is going to give us 1, 1 and 0 is going to give us 0, 0 and 1 is going to give us 0, 0, 0, 0, 0, 0, 0, 1 and 0 is 0. So we're left with our answer being generally just 1 in base 10. If we're converting to base 10, or really just 1 in base 2 also works. 1 is kind of universal. But that's the whole idea with bitwise. You're taking the same rules we learned, same truth tables, the same information, and you're using it on binary. So conversely, if we looked at bitwise OR, which is just one line, the truth table is still the same. This is still the same truth table. Yeah, that's chopped, bro. So I think it might be good if we took this exact same numbers and then now applied OR to it, bitwise OR. If you see 2, you're evaluating true and false. You're not getting a. One thing you can know, at least with bitwise, is it returns a number. Bitwise returns numbers. Logical returns true or falses. They return Booleans. Excuse me. Okay. So what was 34? 1, 2, 1, 2, 4, 8, 16, 32. Wait a minute. 1, 2, 4, 8. Man, I did 35. Okay, we're just making that 35. I don't care. It's always been 35. I don't know what you mean with 34. It was always 35. Okay, anyways, back to the problem, right? So we have 35 or 5, so that's going to be 1, 0, 1. At least I know I did that one, right? Well, or, yeah, 1, 0, 1 is 5, 1, 1, 0, 0, 1, 2, 4, 8, 16, 32. Yeah, okay. Let's make it sure. Alright, well, or is going to apply the same OR rule. So 1 and 1 is 1, 1 and 0 is 1, 0 and 1 is 1, 0 and 0 is 0, 0 and 0 is 0, 0 and 1 is 1. That's going to be 1, 2, 4. So we're going to have 1, 2, 4, 8, 16, 32. Final answer is going to be 32 plus 4 is 36, 38, 39, and base 10. And then y'all just be like this in binary. So it would be 1, 0, 0, 1, 1, 1, and base 2. And you can kind of see how you got drastic outputs. This one gave us 1 base 10, this one gave us base 10, and this one gave us 39 and base 10. Okay, the next operator we're going to discuss is the tilde, which is the bitwise not. So if you remember from our not table, 1 to 0, 0 to 1. Let's look at this as an example. Well, first thing you have to remember before, just move this over here. Anyways, first thing you have to remember is the idea that when you're using a bitwise operator, whatever data type you use or whatever number you're putting in here is automatically looked at as an integer. And integers have 32 bits, which means they have 32 place values. So if you're looking at an integer of 4, the 0 or 1, 2, 4, right here, 0, 0, well, these aren't empty, they're all zeros, right? And then when you flip them conversely, they all become 1s. And this is not 32, but you get the point, and you maybe think, Sid, won't just give me a really, really big answer? You would think that, but you have to remember the concept I talked about earlier in all the way back when talking about 2's complement in basic arithmetic of the signed bit. The leftmost bit is the signed bit, and then what this is it's when your leftmost bit is a 1, you kind of view that as a negative. So if it's like what, negative, let's say 128, you view it as negative 128, and then you'd add and so forth. But I already discussed this previously, so I'm not going to talk too much about it. But if we look at it in this scenario, where we take the leftmost bit, whatever value that integer would have been, 2 to the 32nd or something, and you make that a negative, well then it doesn't really matter how much you add onto it with these positive values, because negative 2 to the 32nd is way bigger than than 2 to the 31st, plus 2 to the 32nd, and so on and so forth, right? So we left with like a small number, which coincidentally you use a formula for. The solution you're left with tilde of n is equal to negative n plus 1. So if you're using tilde of 4 in this scenario, which is what we described, you'd be left with negative 5, negative 4 plus 1. If you're doing tilde negative 4 or something, you'd be left with negative 3, you'd be left with 3. You can actually see how here you're getting a smaller number when using tilde, but when you're going from a smaller number to a bigger number, when you're going from a negative number to when you're noting a negative number, you're going to a bigger number, and that's to do with the signed bit. Because in a negative number, you're already dealing with that leftmost bit being 1, and then you're flipping it to 0, right? So you're making your number bigger as a whole, versus here, your leftmost bit is 0, which is nice, but then you're flipping it to a 1, which is going to make it really small. Excuse me. So that's tilde, and if you want more explanation on this whole signed bit, check out the 2's complement video, because I talk about that a lot. Like a lot. Alright. Now we're moving on to the kind of more interesting ones. Left shift. So left shift looks like this. It looks like you're writing L's or less than signs. And pretty much what it is it's taking that number. So let's say we're doing 2 and we're 2 and I'm writing 2 here. But what's the binary of 2? That's 1, 0. It's gonna shift it back. So it looks something like this, right? And so on and so forth. It's gonna take this 1, 0 and shift it back 2 places. So we're gonna look like this. That's one shift down. And then again, it's gonna shift it again, and now that's 2 shifts down. And you can actually see like your number's gonna get bigger and bigger as it goes on, exponentially bigger. In fact, there's a formula for this, and the formula goes like this. So if we refer to this as A, left shift, N, the formula is A times 2 to the N. This is the formula. So if we're doing 2, left shift 2, we would actually receive 8 as our number, which is, we could do that? 1, 2, 4, 8, yeah, we got 8. Now, you can do the same thing with right shift. So, right shift has these greater than signs. So if we're doing 2 right shift 2 and we're dealing with this, right? So on and so forth, what would actually happen is you'd shift your numbers to the right too. So we'd shift this to the left, to the right one. You get something like this from your first shift, because remember, you can shift to the left a lot, right? You have what, 32 bits in an integer. The right, you don't got any bits. It's kind of like a wall. That 0 is gone, bro. And then we're gonna swap it again, shift it all to the right again. So you're gonna be left with this. It does not wrap around. It doesn't happen. Don't think it wraps around. It just kind of disappears. So the 2 shifts should be left with roughly 0. And does this make sense with the formula, which is A right shift, N is the same thing as A divided by 2 to the N? Well, yes, because if you think about what happens with integers in Java, if we do 2 divided by 4, Java is not reading that as 1/2, it's reading that as 0. So we got 0 here and we got 0 there, so it checks out. Now there's one last concept. We're looking at right shift, right? You're looking at right shift of your numbers. And let's say something like this. And I'm just shifting it to the right. Well, when this moves to the right, you know, we lose a 0 in the process, so this 0 is gone away. Just like how in this, we lost that 0. Or that's left shift, sorry. In this, we lost that 0 and we lost that 1. In this case, we're losing that 0. And we keep shifting, right? And as we keep moving to the left, we gain zeros on the right. But it's not actually zeros we gain. That's a misconception if you think it's just zeros. This is what we call the signed right shift. And then so what that means is if your A, if I'm working with a positive number, if your A is positive, then you're going to fill in that right space with zeros because your rightmost bit, your leftmost bit should maintain sign. It should maintain the sign. If it was positive here, that means your leftmost bit was a 0. Then we gotta fill it up with 0 so we can maintain that sign. Conversely, if I had a negative 2, and that was my leftmost bit, and that was my A, so my A is negative. Well, in order to maintain sign now, instead of filling up the gap with zeros, I need to fill it with 1s. So we're gonna add 1s, and this would also all be 1s too. So let's just do something like that. I mean, I'm not gonna write out the choose. I guess I probably should. Because how many acronyms I do it. Choose complement version of 2 is kind of like you take 2, this, and you just pause here and you just flip all of this and stuff. You leave that. There you go, that's 2's complement done. I talked about it, I had a video on it, so I'm not really going to go into how this is, or more detail. But anyways, you go up to 32, right? And as you keep shifting this way, instead of adding zeros, you're going to be adding in ones because we did it with negatives. We have to preserve the sign. And if the sign's negative, that means the leftmost bit was negative. So that means we have to add in, sorry, if our sign was negative, that means our leftmost bit was a 1, which means in order to maintain that leftmost bit of 1, we have to keep on adding ones. Just like how when we were dealing with a positive 2, we added zeros because our leftmost bit was a 0. So in order to maintain that 0, maintain that positivity, we have to keep on adding zeros to ensure our leftmost bit would be 0. So if that was a little bit over your head, it's going to be like this. If your A is positive, well, the formula is still true. I'm just saying this so you understand. The formula is still true. The formula holds no matter what. That's still true. But when your A is positive, you're going to fill your back with zeros. When your A is negative, you're going to fill your left side with ones. Now, the reason why I'm talking about this is because there's a concept called the unsigned right bit, which is this. That is left bit. Right bit is the gradient sign. This is unsigned. It automatically will always fill your left side with zeros, even if you have a negative. Doesn't matter. So if I put a positive 4 in here, like I don't know 1 0 0 0 0, well, you probably wouldn't be able to tell any difference. It'd probably just feel the same because, oh, what's 1 with 0 in here, right? Who cares? My number's getting smaller. Life is sad. However, this is a big however, okay? I don't know if it's true, but for positive numbers, I'm gonna assume that you can positive numbers for triple right shift or unsigned right shift, the rule applies. A over 2n applies. For negatives, this is not the case. Because now look, I have this really long negative. And I have this leftmost bit is negative. Well, watch what happens. When I shift this to the right, I delete this. Because we're doing unsigned, we're going to fill that in with 0. And now suddenly this is going to be positive. And remember I was talking to you earlier about how, if I can find it, negative 2 to 32, because it was so negative in fact that it was able to counteract the whole adding the positive 2 to the 31, 2 to the 30th, all that they were adding, right? It was so negative that I was able to counteract that whole sum to ensure our number was still relatively small. Well, now we're saying bye to that negative. We're saying bye to that negative 2 to the 32. We're making it a positive 2 to the 32 now. And then we're adding that with 2 to the 31. So our number is going to be really, really big. I couldn't even tell you what it is. Just for negatives, if it's unsigned right shift, you're getting a really big number. There are 2 more Boolean laws I forgot to mention that I'm going to discuss in this video. So some Boolean algebra that I haven't covered yet. There's 2 more laws. The first is the law of the disappearing opposite. So what this means is if you had a plus a naught b, you can silence this term or make it disappear and you'll have a plus b. And then if you have a naught plus ab, well, now the opposite is a because it's the opposite of this a naught. So we can silence that and we can get a, or make it disappear, and we get a naught plus b. The key thing to realize with this law is If the two values are the same, they're both A except one is the opposite of the other, we can just get rid of that opposite value and we will get this. That's a law of the disappearing opposite. The next isn't really a law, but it's a continuation on De Morgan's. As I forgot to bring up the OR to XOR. So as we saw, De Morgan's for the AND condition gave us NAND, OR gave us A naught plus B naught, and then the De Morgan's for the OR condition gave us NOR, or gave us A B naught. The condition for the XOR will give us NOR, or X NOR. But in order to figure out what this is, we first need to understand what XOR equals. XOR, or looked at as a circle plus B, I guess, is also represented as A B, or sorry, it's also represented as A naught B plus A B naught. And then if we find the XOR or XNOR of this, all that is taking this expression, so XNOR would be the nodding or negation of A naught B plus A B naught. So by applying De Morgan's onto this, we will be given A plus B naught multiplied with, or anded with, A naught plus B. By further factoring this out, we will get A times A naught plus A B plus A naught times B naught, and I like having my knots in blue, so I'll do that. A naught B naught, and then finally plus B naught. So just like this. So if we were to evaluate this, due to complement's law, this will cancel out. This would also cancel out due to complement's law, like this. And you will be left with A B plus A B naught. And that'll be your XNOR. And this doesn't cancel with complements. We know complements for A plus A naught equals 1 always, but that is not entirely the case here. This is due to the fact that for an AND, 3 possibilities give you 0 and only 1 give you 1. But if you have, so the 3 gives you 0, 1 gives you 1 if you're working with 2 variables, but for an AND with just 1 variable, then it's just 1 for each. All I'm trying to say here is that just with more variables, the expression gets a lot more convoluted. However, this is not true when you're working with something like this. AB times AB naught, however, is still 0. Because if you're thinking about it logically here, no matter what this is, no matter what AB is, if we're taking AB, and this even gives you true or this gives you false, if you're multiplying that by the naught of it, then no matter what it is, you're going to get, if AB is true, you're going to get times false. If AB is false, you're going to get times true. So you're going to get 0 or false either way.